This conference will now be recorded.
Very good evening, students. Yesterday we had started with the Gauss's law. Today we will continue with Gauss's law. So today's topic is Gauss's law and its application. Applications. Okay. So first of all, see what we have learned so far. We have learned potential calculation, electric field calculation due to electric dipole, point charge, system of charges, etc. And we have seen equilibrium of dipole. If I just briefly discuss about this, see we can have dipole P, dipole moment in this direction. Suppose this is electric field, or we can have both in the same direction. Okay, electric field and P. So we know the potential energy is PE minus P cos theta. So when we have this minimum, that position is called equilibrium, stable equilibrium. So that is possible only when this is 1. So this is actually having minimum energy. So when theta is equal to 0, that means both electric field and the dipole moment are in the same direction. That position is actually called stable equilibrium for a dipole. Okay, and this is also an equilibrium, but this is actually, say, this will give you plus PE. So that is also one kind of equilibrium anyway. So that is unstable equilibrium. So in this case, the force which like torque is not restoring type, not restoring torque here. The torque act here on this dipole due to this electric field is not restoring type. Restoring type. It acts in the opposite direction. Okay. Okay. So, and in this case, actually, torque is restoring type. Restoring type. So this is actually fundamental idea about this equilibrium of dipole. Now we'll directly go to the topic, Gauss's law. We had somewhat discussed yesterday, but we'll just recap somewhat to understand that matter better. And also we'll go for mainly the application part and some intricate points which I will discuss about Gauss's law. Okay, so what is Gauss's law? We have already discussed electric field calculation, etc. So why do we need Gauss's law? Gauss's law is actually a simple method to calculate electric field, but is it applicable for everything, every charge distribution, everywhere? In principle, it should be applied everywhere, but it applies, so it applies well where there is a symmetrical charge distribution. Okay, where there is a symmetrical charge distribution, that means and also you might be very much familiar by now, in physics always you go for symmetry, like say we can have planar symmetry. Okay, planar symmetry. We can have spherical symmetry. We can have cylindrical symmetry. So these are some of the symmetries which we look for. So whenever we have such symmetry in the charge distribution, we can apply Gauss's law, and in that case calculation of electric field will be so much simplified. Okay, we'll just before we discuss about Gauss's law, first let us see what is called flask, electric flask. So if you understand the meaning of flask now, it will be easier to understand Gauss's law in magnetics or magnetic flux. So actually, see, we have seen that electric field generally, what to say, visually we represent by electric field lines. So magnitude, its length of this gives the magnitude or strength of the electric field, and direction gives the direction of the electric field. So these are called field lines. You might know this. So electric field lines. Now, what is electric flask? Suppose I have a point charge here. I'm just considering a point charge. Obviously, point charge will see electric field lines will be passing like this. All right. So if I have a surface, plain surface here, then these field lines will be passing through this. Okay, passing through this surface area, right? So this surface area is actually, see, the field lines are horizontal and the surface area is kept vertically or perpendicular to the horizontal plane. You can actually think of this as y and this to be z, yz, and let us say this is, yeah, somewhat x. So this is horizontal. See, this is actually the base. This is the vertical plane. So this is called field line crossing or field line passing, crossing the surface area. Field line crossing the surface area. This is called actually field lines. Field line crossing the surface. Now, what is flask? Flask is the number of such field lines which are crossing the surface area, which is actually kept perpendicular to the direction of the field lines. Okay, so if I, okay, let me just write this definition. So number of field lines, okay, number of field lines, it is actually measured by number of field lines electric field lines, also you can say electric field lines crossing a surface area placed perpendicular to the perpendicular. Actually, this cannot, okay, let me not write this. So crossing surface area, because this is not the general formula, the general definition. Surface area, let us write the surface area, that's all. Okay. So what is this flask then? It is actually measured by number of field lines crossing a surface area. Okay, so surface area, suppose my field lines are like this. So surface area can be kept just, suppose, at an angle like this, at some angle like this. Okay, some surface area kept at an angle. Okay, let me just do it in this way. So this is surface area. Okay, or just a minute. This is surface area, say surface area in this direct, like oh sorry, this is the electric field, and surface area kept in such a way that its normal is like this way, surface normal. Okay, so maybe the surface is kept like this. Okay, let us keep the surface like this. Okay, and field line is crossing like this. So this is n cap. N cap is the direction of the surface. So this, see, always, okay, before I draw this, let me just write the mathematical uh, expression for the flask. It is denoted by phi, and it is written as, if suppose if I take a small area through which the electric field lines are passing, then I'll write d phi, and it is actually E dot ds. If the area is small area, ds, E dot ds. And if you want to find the total flux, so you have to go for integration or summation of a small area. Okay, so d phi, sum integration d phi, this is E dot ds. Okay, you might be thinking, what is this ds? And also it is vector. So ds is actually the area vector. Okay, this is area vector. That means area has both magnitude. What is the magnitude? Magnitude is just the value of the area, and it has direction as well. What is the direction? Direction is actually the n cap. N cap in the sense, see, it is the normal to the surface area. That is the direction. But which direction we should take? The normal. Suppose I have surfaces like this. Okay, so I have surface like this. So should I take inside? This is normal, or should I take outside? This is normal. Okay, in this case, we need to remember two things. If the area is open, so open area, suppose I have a plain sheet of paper. A plain sheet of paper is an open surface. Okay, it has two surfaces but open surfaces. Okay, or you can just consider one surface itself. Okay, so I can take such open surfaces like normal for this open surface in any direction, either in, see, on the other side or this side, doesn't matter. So that is actually the direction of the area. So that is called area vector, direction of area vector, or that is actually called normal to the surface. So normal to the, suppose I have a surface like this. Okay, some surface like this, so normal will be this way. If it is open, I can take the normal this way also, doesn't matter. Okay, but suppose I have a football, this is closed surface. Okay, so this surface normal has to be always outward normal. It should not go like this. This is not the case. Okay, so normal has to be taken in place of closed surface. So in case of open surface, I said open surface, and this is closed surface. So in case of open surface, the normal to the area should be taken in case of open surface in any direction. Okay, okay, but in case of closed surface, you should take outward normal. This is the convention. So look what we have got in this case. So suppose this is surface area, and normal to that is this direction, n cap. Generally surface, see, phi, I am writing total phi. So E dot ds could be written in this way also, E dot n cap ds. N cap is the unit vector along on the surface area. Okay, so E dot n cap ds, like that we write. So n cap is the perpendicular or normal to the surface area, as I had discussed so far. For closed surface, you have to take outward normal. For the open surfaces, you should take in any direction. We could have taken this direction also. Okay, but one point here we need to remember: while rotating the surface, the normal should not change. All right. So in this case, look, the n cap. See, this is a dot product, right? So can I write this as E ds cos of theta? N cap has unit magnitude. So this is ds cos theta. Okay. So simply, if we write, this is Es cos theta. very simplified form of flask, mathematical form of flask. So this is dimensionless. This has dimension of area. This has dimension Newton per coulomb. Okay, so we can write Newton per coulomb into meter square. So this is the unit of flask. Unit of flask. Unit of flask. Sometimes some competitive exam you might be asked to find out what is the dimension. Okay, what is the dimension of the flask? So unit of flask is Newton per coulomb into meter square. Okay. So this could be written even volt into meter also. Volt into meter. Okay, volt into meter. All right. Because see, electric field can be written as voltmeter, voltmeter. Sorry, volt per meter. Electric field can be written as volt per meter. Unit can be written as volt per meter. So in that sense, it can be written. Unit can be SI unit can be written as volt into meter or Newton per coulomb into meter square. So these are SI unit of 5 plus. So in this case, look, the flask depend on the angle between what? Between the area normal or area vector and the electric field. In this case, this is theta. So we have got ES cos theta or EDS cos theta in this case, EDS cos theta because DS is the surface area here. All right. So see if the surface area, see if I just take this electric field tangentially, that means just parallel to the surface, then this theta will be 90 degree in this case. If theta is 90 degree, what will be the flask? The flask will be 0, right? If electric field also taken in this direction, okay, in this direction, so such case theta will be 0, so flask will be maximum E into ds. This is maximum flux. Okay, so look, we are writing here. If this case, see this case, the flask is maximum flux because the area normal, see ds also has the direction in this way also, and in this case look, ds is this way and electric field in this way, so 90 degree, so flask is 0. So this is called tangential. So this flask is tangential to the surface, this is normal to the surface. Okay, so electric field, when the electric field is tangential to the surface, flask will be 0. When the electric field is perpendicular to the surface, then flask will be maximum. Okay, see, to calculate electric flask is important in while applying Gauss's law. Otherwise, see, Gauss's law is nothing. Okay, so calculation of electric flask will be critical sometime. So to calculate electric flask, we need to remember few things. We need to take care the following things. What are those? First point is that electric field component of the field has to be taken perpendicular to the okay, so perpendicular to the surface always. This should be always, okay. E has to be taken perpendicular to the surface. To the surface. Okay, and second thing is this, that whenever we calculate flask, about or through any surface, so flask has to be, see, the electric field has to be always constant. Electric field has to be constant to the surface. In this case, look, this electric field lines are having the same strength, E everywhere E. So then only we will be able to calculate flask. We should not, our electric field itself should not vary. So E has to be constant. E has to be constant. Constant over the surface, or constant at each point, at every point on the surface. On the surface. Okay, so this is the point we should remember. All right. So like, see, in this case, so this is, see, here you will get maximum flux both cases. Okay, so this is actually open surface. This is open surface, open surface. We can calculate flux for open surface as well as closed surface. This is closed surface. All right. So look here. See, in this case, flask is, see, electric field E. Electric field is tangential to the surface. Tangential to the surface. Tangential to the surface. Here also, see, the electric field is actually tangent to the closed surface. This is open surface, this is closed surface. So both cases actually phi will be 0. We have already discussed why. Now let us come to the point, that is Gauss's law. Gauss's law. So what is Gauss's law? What is the statement of the Gauss's law? The net, see, Gauss's law actually builds a relationship between the flask, okay, a relation between the flask and the charge enclosed by a closed surface. Closed surface. So it builds a relationship between the flask through a closed surface and the charge enclosed by the closed surface. So the net flask through any closed surface is equal to the net charge inside the surface divided by epsilon 0. So if I mathematically write this, so mathematically Gauss's law can be expressed as flask. Okay, so let me write this. Integration E dot ds, this is flask, right? We had already seen. And closed surface, this is equal to the charge enclosed divided by epsilon 0. So this is the mathematical expression for Gauss's law. Okay, so this is actually called closed surface integral. Closed surface integral. Surface integral. Okay, all right, let me go to the point. See, Gauss's law can be used to evaluate. Okay, let me write Gauss's law here, mathematical form. So mathematical form of Gauss's law is this: charge EMC means enclosed by the closed surface. Okay, this is dot product. So Gauss's law can be used to evaluate the electric field for a charge distribution which has specific symmetry, either planar symmetry or spherical or cylindrical symmetry. Now see, we'll go for application. Before we apply this, we need to know a little bit of what are the properties of this law and all. So see this Gauss's law. Here you can see this side is total flux. This is the total enclosed force by the closed surface. Okay. And see, while calculating flux, I had said already that the electric field should be constant at each point on the surface we have taken, right? So the surface, okay, let me just tell you something. So in this case, see, when we apply Gauss's law, we will actually always draw a Gaussian surface as the closed surface. Okay, closed Gaussian surface. So what is Gaussian surface? Suppose I have been given to calculate electric field due to a particular charge distribution. Okay, charge distribution. So I need to actually consider, I need to consider a closed surface which is enclosing the given charge distribution. Either it is a charge distribution, continuous charge, or maybe point charges. Okay, so you have to always draw a Gaussian surface. So what should be the property or characteristics of Gaussian surface? It must be closed surface. It that point inside. Okay, such that point charges will be inside points. Okay, so such that the points inside, on and outside the surface may be distinguished clearly. That means, see, my Gaussian surface should not go in this way that there is a point charge here q1, and very close to that there is another point charge, but the Gaussian surface is going passing through them. But it is not possible. So Gaussian surface should not go on any isolated charges. Okay, Gaussian surface should not be drawn on any isolated charge. Okay, it can go. So Gaussian surface can go through the continuous charge. So Gaussian surface should not be drawn on an isolated charge, on any isolated charge, on in the sense passing through. Okay, drawn through any isolated charge. However, it can go through or pass through. However, it can pass through continuous can pass through it can pass through any continuous charge distribution. Okay, continuous distribution of charge. All right, and second thing is that the surface must pass through the location where we calculate electric field due to the given charge distribution. So the Gaussian surface will take must pass through the point where we are calculating electric field. Okay, due to the given distribution of charge. All right, so we'll just go. We'll just take applications, real applications. So where we'll be showing you how we are drawing Gaussian surfaces, what are the symmetry of the Gaussian surfaces. Okay, so like in this case, electric field due to a point charge we will be discussing today. So electric field, see, we know electric field. Suppose I have a point charge plus q, so electric field at any distance r, we know this. We know this result. What is this result? So electric field here will be q by 4 pi epsilon naught r square. Okay, so this is the field, right? But how to calculate? Applying Gauss's law. See, to calculate this electric field due to point charge, we have to draw first. We have to draw a Gaussian surface. surface with proper symmetry, through the point where electric field has to be calculated. This is the first point. Okay, so let us see here. So this is here actually the Gaussian surface. So according to the symmetry, see, point charge has spherical symmetry. Okay, so point charge, how, I'll tell you, has a spherical symmetry. I'll tell you why. Symmetry. Okay, because see, if I calculate electric field at any fixed distance from this point charge, that will be always same everywhere. See, so this distance, if I just, this points, if I just connect all of them, then I get a spherical or spherical surfaces. Okay, so that's why it has got a spherical symmetry. So I have drawn the Gaussian surface as a spherical cell or spherical surface. Okay, spherical in nature. So you can see the Gaussian surface is now a sphere. Okay, a surface of a sphere of radius r, small r. Here the Gaussian surface is the surface of the sphere, surface of a sphere of radius of a sphere of radius r, because at r distance I have to calculate electric field, that's why. So once we get this spherical surface, then can we find out the flask? That is the question. We know, so this is the simplified formula of Gauss's law. This is simplified Gauss's law, simplified equation of Gauss's law, simplified form of Gauss's law. Gauss's law. So that is the flask, total flask passing through the surface, closed surface. So E into S, that is equal to Q by epsilon naught. So why ES? Because I have to always take the electric field perpendicular to the surface. In that direction I have to take. That's why I have taken directly this. Okay. So what is this Q? Q is the charge which is enclosed by the surface area here, or surface, closed surface here. So here the closed surface has this. Okay. So Q is the charge which is enclosed by the closed surface. So always we have to enclose the charge, whether it is single point charge or the charge distribution, with a suitable symmetrical Gaussian surface. Okay, then we have to calculate the flask, and that flask will be the charge enclosed by the sphere divided by epsilon naught. So in this case, look, I think I'll erase everything. I'll just keep this thing. This is Q by epsilon 0. So I have to find out this side. So see, electric field at a fixed distance r, it will be always constant. It is not varying. So I will write E is the field, suppose at each point. And what is the S? S is the surface area for this sphere. So that is 4 pi r square. Okay, so this is the flask, total flask through the surface area. Okay, then this will be exactly equal to Q by epsilon naught. Epsilon 0. So where Q is the charge enclosed by the surface. And see what we get. Four pi epsilon 0 r square. Sorry, this epsilon 0 I'll just keep now itself. So you look for point charge, we know this is the electric field. While calculating using Coulomb's law, etc. So we have got Q by 4 pi epsilon naught r square the same. So Gauss's law is actually more general and powerful tool to calculate electric field, but only thing is that you need to know the symmetry so that you can find out the flask properly. Now we'll see the application of Gauss's law for linear charge distribution. So linear charge distribution has see charge density. This is lambda. Lambda is coulomb per meter. Coulomb per meter. Coulomb per meter means this is charge per unit length. So charge per unit length. Total charge by total length. Okay. All right. Charge per unit length. All right. So this is actually denoted by lambda. Charge distribution lambda is equal to Q by L. So this is the linear charge density. Now look, so this is, so suppose there is an infinitely long wire. This is the wire which is actually positively charged. Now for such wire, if suppose, okay, if for such wire, you need to calculate the electric field at certain distance r. So this is the point, suppose this is the point where we have to calculate the electric field. So that is at r. And what is this? This has actually line charge distribution. Okay, line charge distribution. So this line charge distribution will produce a field at P that we have to calculate. Okay, so fine. So how to find out the electric field? So let me write down the Gauss's law. So very simplified form, E into S charge enclosed by epsilon 0. So this is the simplified form of Gauss's law. Now, so in this case, when I have linear charge distribution, so linear charge distribution always has cylindrical symmetry. Linear charges or linear object, linear charge distribution or any linear object linear charge distribution must actually has a cylindrical symmetry. Cylindrical symmetry. So linear charge distribution has cylindrical symmetry. That means Gaussian surface, Gaussian, sorry, Gaussian surface will be of cylindrical in shape. So Gaussian surface cylindrical in shape. Okay. So in this case, look, this is the linear charge density. Sorry, the line charge distribution. So I have considered Gaussian surface as a cylindrical surface, coaxial cylinder. Okay, so Gaussian surface. So this is the cylindrical Gaussian surface. See, it is infinitely long, but I have taken Gaussian surface, Gaussian surface, Gaussian surface of cylindrical shape, and the length of the cylinder has been taken as L. Okay, L is the length of the cylinder, not the wire. Wire can be infinite. Okay, so in this case, see, I have to calculate the flask through all the surfaces. See, I have three surfaces actually. See, I have three surfaces. See, there are three surfaces. So one curved surface, and see there will be two plane surfaces. Two plane surfaces. See, this is one plane surface. Another plane surface is this one. Okay, this is another plane surface. So two plane surfaces, and I have curved surface. This one. Look, this is the curved surface. Curved one. Okay. So cylinder has three types of surfaces, or three surfaces, I can say. So to calculate the electric field, we need to first find out the flux, electric flux, total electric flux through the surfaces or closed surfaces, which is actually enclosing the charge distribution. So in this case, you look, since I have three surfaces, I have to calculate flux for three surfaces as well. So flux, suppose flux phi 1, okay, for phi 1, suppose phi for curved surface, and phi for plane surfaces, okay, p1, one plane surface, plus for another plane surfaces, okay. So this will give you the total flux es, okay. So this will be total flux first of all. So see, I have taken, see, let us say this plane surfaces. So these plane surfaces, by symmetry, the electric field lines will be like this. See, they will be actually radially outward. These are the electric field lines. And what about, so see, these field lines are actually, electric field lines are electric field lines are tangential here to the surface, tangential to the surface. Okay, tangential surface to the surface, that means you know what is the flux here. So the angle between E and E actually perpendicular to N cap. Okay, so flux will be how much? Flux will be E ds, right? E ds. So this will be actually 0. Flux due to these plane surfaces will be 0. So flux due to these plane surfaces will be 0, because the electric field line actually is becoming, or electric field is becoming tangential to these surfaces. Okay, now I have left with the curved surface. So if you have your electric field lines radially outward, then you look, this electric fields are actually perpendicular to the surface. So see, electric field lines are perpendicular to the surface, to curved surface. So perpendicular to the curved surfaces. Okay. So in this case, actually there will be maximum flux E into S. What is E? E is actually the electric field I am just considering, and which has a constant value at each point on the curved surface, and the surface area of the curved surface. Okay. So what we are doing, see, curved surface area is how much? See, S will be here, 2 pi r into L. L is the length. The length of this cylindrical Gaussian surface. Suppose small r is the radius of this. So you look, this is the surface area, 2 pi r into L. Okay, once you get this, see, I can write the Gauss's law, applying Gauss's law. E into 2 pi RL, this is E into S, divided by charge enclosed. See, what is the charge enclosed? I have taken, see this. See, first of all, you need to understand the charge may be so much for infinite this charge distribution. So this is infinite, so it may have a very large amount of charge. But what I have to consider here, the charge, this is enclosed. Okay, charge enclosed by this Gaussian surface. So if the line charge density is lambda, then the charge enclosed by this curved surface will be lambda into L. So lambda into L. See, infinite long wire may have like charges. The amount of, like, large amount of charge, but what I have to consider, the charge enclosed divided by epsilon naught in the right hand side. So in this case, see, this LL goes off. So what we get actually is lambda by 2 pi r epsilon naught, lambda by 2 pi r or 2 pi epsilon naught r. Okay, that means what? That means the electric field line, electric field actually is inversely varying. Okay, it is varying inversely with the distance. Okay, distance from the axis of the cylinder, or from the distance of the infinite wire. So this is the curve, necessary curve. Okay, how electric field vary for a cylinder. Okay, now we'll go to another application, that is electric field due to a plane sheet. So when I have, so this plane sheet actually infinite or infinite plane sheet, infinite plane sheet, plane sheet. For infinite plane sheet, what is the symmetry? Anyway, the symmetry is planar, but how to take, or what is the Gaussian surface you may be taken, Gaussian surfaces. So Gaussian surfaces, you have to take either Gaussian pillbox, Gaussian pillbox, or a rectangular. Okay, uh, rectangular Gaussian surfaces also can be taken. But in this case, see, I have taken in such a that, see, this has very small length compared to, okay, so this is very small length. So you look, I have taken this Gaussian, see, this is Gaussian pillbox. Just at the surfaces, this space is just at the surface. This is actually exaggerated to show you how we take Gaussian pillbox, and what it is also actually in terms of cylindrical symmetry. And you know, the Gaussian surface has to be taken up to the surface itself, so just upper surface of this, and here also just this one. Okay, so Gaussian pillbox is just, see, it has very short length. It doesn't have a much above length, much above this plane surface anyway. So in this case, see, the surface charge density is sigma. That is the distribution of charge in a plane. Okay, surface charge density is sigma. Sigma is actually surface charge density. So this is surface charge density. So what will be the total charge on the surface? So we can write actually sigma into the area of the whole surface. Okay, so in this case, look, I have to calculate the flux through the Gaussian surface, closed Gaussian surface. So I have two surfaces here. This is surface 1 and this is surface 2. Okay, so I have to find out the net flux. Okay, so net flux I have to calculate. So how to find out net flux? Let me tell you here. So I have to find out net flux. Find net. So how to find out that? See, I have flux. So this is the surface of the plane sheet. Okay, infinite plane sheet. So electric field has direction this way also, as well as this way, because this is a positive charge. So electric field will be going outward radially. Okay, so positive charges means, okay. So we know flux will be E into S. E is the electric field, and S is the area. So suppose this area has S0. Okay, S0. The Gaussian pillbox has area S0. Okay, and this flask is this way. I'm taking as positive this side and I'm taking negative this side. If I take that, then see I can write E, this is S2. S2 means S only. In both cases it is S. ES, the flask in this rightward direction, minus of minus in the left hand direction. That's why this minus comes. So net flask is how much? Since it is moving in opposite direction. And see, so this is S1. So this you will get actually ES1 plus ES2. These are the plus. So S1 anyway, Gaussian pillbox has the same area. So I can write 2ES. This is the total flux or net flux enclosed by this Gaussian surface. So you might be now thinking whether there will be a flux through this way. No, here also you will see that electric field lines are actually tangent. Sorry, electric field lines. Yes, electric field lines will be tangential to the surface. So that's why there will be no flux. Okay, so I have got the flux, and this according to Gauss's law, what I have to write according to Gauss's law, net flux must be equal to the charge enclosed divided by epsilon naught. So what is charge enclosed here? Charge enclosed means, sorry, in this case charge enclosed will be sigma into S, that is the charge enclosed charge. So sigma S is the enclosed charge, sorry, enclosed charge. So enclosed charge is sigma S. So I can put this divided by epsilon 0. So this is actually Q enclosed. So I can write 2ES this can be cancelled out. So E will be sigma by 2 epsilon 0. And this value will be always constant. So you can see that this has no dependence on the distance, dependence on the distance from the charge distribution. Okay, from the charge distribution. So this is actually always constant. At any distance you will get the same value, this. Okay, at any, but there will be always a direction for the electric field. Generally infinite plane surface is not obtained in general. So infinity is not realizable in real world. But in case you have a very large plate like parallel plate capacitors, so in those cases, suppose this is having positive sigma, so electric field here will be 0. I'm sorry, this will be sigma by epsilon Yeah, so electric field lines will be, I'll just go here. If I have two plane surfaces, suppose here, so my point is that whether I can think any plane surfaces as infinitely long and we can infinite planes it and then I can use this result or not. Answer is yes, as long as your uh, the dimension of this plate is much greater than the distance where you are calculating electric field. So in case of this, the separation is generally taken very, very small. So electric field lines, in case of, say, if this is positive sigma, this is negative sigma, then electric field will be 0 here, and also here it will be 0. But in between the plates, there will be existing uniform electric field. Okay, so this side and this side is 0. This will be having sigma by 2 epsilon 0 electric field, sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. Both will give you sigma by epsilon 0. Okay, so this will be the electric field at, see, inside this. Okay, we'll discuss this in the next class. Further, we'll actually take up various applications of Gauss's law from various competitive exam question paper, and then we'll proceed further. Okay, so thank you for your patience. Bye for today.